Hello, students. Let's begin with a thought. Have you ever admired the intricate patterns on floor tiles or the bricks stacked neatly in a wall? What you see is repetition, and nature too builds its solids with repeating patterns. In chemistry, this repeating arrangement of atoms, ions, or molecules in three-dimensional space is called a crystal lattice. Each small repeating unit in this lattice is known as a unit cell. So, just like a single brick can represent the design of an entire wall, a unit cell is the building block of a crystal. Today, we will uncover how solids gain their orderly structure by studying space lattices and unit cells.
A space lattice is essentially an infinite network of points, each point representing the position of a constituent particle. Imagine graph paper extended infinitely in all directions, but in 3 dimensions. That's how a lattice behaves. Each point in a lattice has the same environment, meaning the arrangement around it is identical. This regularity explains why crystals like sodium chloride show such symmetry. In the NaCl structure, sodium ions and chloride ions alternate in a highly organized way, producing a cubic pattern that repeats throughout the solid. It is this repeating geometry that gives solids their definite shape and external crystal form. Now let's zoom into the smallest representative of a crystal, the unit cell. A unit cell is the tiniest portion of the lattice that, when repeated again and again in all 3 directions, generates the entire crystal. It is characterized by 3 edge lengths, denoted as A, B, and C, and 3 interaxial angles, alpha, beta, and gamma. The entire beauty and complexity of a crystal can be reduced to this small unit. Think of floor tiles. One tile contains the pattern, and by repeating tiles, you cover the floor. Similarly, the repetition of a unit cell builds the entire crystal. It's fascinating to realize that the symmetry of a whole diamond or salt crystal is hidden in the geometry of a single unit cell. Not all unit cells are identical. Based on how particles occupy positions inside them, we classify them into primitive and centered types. A primitive unit cell has particles only at the corners. In a body-centered unit cell, in addition to the corners, one particle lies right at the body center. In a face-centered unit cell, particles are present at the centers of each face along with the corners. And in an end-centered unit cell, particles sit at the corners and also at the centers of opposite faces. For example, sodium chloride crystallizes in a face-centered cubic unit cell, while cesium chloride crystallizes in a body-centered cubic unit cell. These variations in packing directly influence physical properties like density, melting point, and stability. Nature allows unit cells to organize themselves in only 7 possible geometries, known as crystal systems. These are cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, hexagonal, and triclinic. Each system is defined by the relative values of A, B, and C, the edge lengths, and alpha, beta, gamma, the interaxial angles. For example, in a cubic system, all edges are equal and all angles are 90 degrees. In a hexagonal system, 2 edges are equal, the third is different, and the angle gamma is 120 degrees. Real-world examples include sodium chloride in the cubic system, potassium nitrate in the orthorhombic system, and graphite in the hexagonal system. These 7 families, called Bravais lattices, are the mathematical backbone of all crystals found in nature. Interestingly, each crystal system can accommodate 1 or more types of unit cells. For example, the cubic system can exist as primitive, body-centered, or face-centered. The orthorhombic system can even have 4 types: primitive, body-centered, face-centered, and end-centered. The combination of the system and the type of unit cell decides the exact geometry of the solid. This is why sodium chloride is face-centered cubic, whereas cesium chloride is body-centered cubic, even though both are salts. Such details help chemists calculate important properties such as density, coordination number, and stability of crystals. So let's quickly recap. A crystal lattice is a three-dimensional arrangement of particles represented by lattice points. The smallest repeating portion of this lattice is the unit cell. Depending on how particles occupy positions, unit cells may be primitive, body-centered, face-centered, or end-centered. Crystals belong to one of 7 systems, each defined by axial lengths and angles. And each system may contain different types of unit cells, giving rise to the rich diversity of crystalline structures we see in nature. I hope this discussion has helped you appreciate how something as small as a unit cell explains the perfect symmetry of a diamond or the structure of common salt. In the next session, we'll explore how to calculate the number of atoms in a unit cell and relate it to measurable properties like density. See you in class.